Hey everyone, and welcome to This Explainer. I am so thrilled you're joining me today because we're going to visually map out some incredibly fascinating source material about a true unsung hero of modern technology. We are talking about a technical ceramic called Cordierite. It's kind of obscure, sure, but it's an absolutely vital material that silently powers our world, literally keeping our engines clean and our data moving fast. Let's just dive right into it. So think about this for a second. What invisible material cleans our air and connects our calls? It sounds like a riddle, right? Like, how on earth can a single material bridge the gap between surviving the harsh, fiery environment of your car's exhaust and the ultra-precise, high-frequency telecommunications of a modern smartphone? Well, the answer is all in the atomic structure of Cordierite. And today, we're going to break down exactly how it pulls double duty. Here's a quick roadmap for today's explainer. 1. The unseen engineering hero. 2. Cordierite's thermal superpower. 3. Crafting the perfect recipe. 4. Shaping the ceramic. 5. From cars to electronics. And finally, 6. The sustainable high-tech future. All right, kicking things off with Section 1, the unseen engineering hero. To really understand how this material went from being just a simple rock in the ground to an absolute engineering powerhouse, we got to rewind a bit. Back to 1813, actually. Cordierite wasn't always this high-tech marvel. It started out simply as a mineralogical discovery by a French geologist named Louis Cordier. But the real game changer? That happened in the mid-20th century. Pioneers at Corning Glassworks, specifically inventors Irving Lachman and Ronald Lewis, realized this stuff had incredible industrial potential, specifically for automotive emission control. It was a massive leap forward. And today, that evolution is moving at a breakneck pace. Cordierite is expanding rapidly into advanced 3D printing and 5G, even 6G electronics. Okay, but what exactly is it? At its core, Cordierite is a magnesium aluminum silicate ceramic. If you want to get technical, it's characterized by the chemical formula 2 parts magnesia oxide, 2 parts alumina, and 5 parts silica. But what's really fascinating here is where this material sits chemically. In the complex ternary phase diagram of magnesia, alumina, and silica, Cordierite is what material scientists call an incongruently melting compound. Now, what does that mean for us? It means it doesn't just melt smoothly into a liquid of the exact same composition. Instead, if it gets too hot, it breaks down into other phases like mullite and glass. So yeah, this unique chemical nature makes it incredibly tricky to work with. But as you'll see, mastering this balancing act pays off immensely. Moving right along to Section 2, Cordierite's thermal superpower. So why do engineers even go through the trouble of mastering this tricky compound? Well, to understand its power, we have to look at its crystal structure. Cordierite is a polymorph, which basically means it can take on several different crystal forms depending on exactly how you heat it. You've got metastable mu cordierite forming below 900 to 1,000 degrees Celsius. Then there's the ordered beta cordierite, which is the low-temperature stable form. But the MVP here? That is alpha cordierite, also known as indiolite. This hexagonal, high-temperature stable form is the undisputed industry standard. It's this specific disordered arrangement of aluminum and silicon atoms within the crystal lattice that unlocks the ceramic's absolute greatest physical trait. And that trait is perfectly captured by this incredibly tiny number, 1.5 times 10 to the negative 6th per Kelvin. That is Cordierite's coefficient of thermal expansion. In plain English, when you heat this material up, it barely expands at all. In fact, along certain crystal axes, the thermal expansion is basically near zero. This insanely low expansion rate gives Cordierite unmatched thermal shock resistance. I mean, you can blast it with fiery exhaust gases, plunge it into freezing cold temperatures, and it just won't warp, crack, or shatter. It is literally a thermal tank. Which brings us to Section 3, crafting the perfect recipe. Knowing the chemistry is one thing, but how do manufacturers actually make this stuff at a massive commercial scale? Well, making Cordierite requires a very specific mix of raw materials. Traditionally, engineers blend naturally occurring minerals, talc to get magnesia, kaolin clay for silica and alumina, and refined pure alumina powders. But here is the really brilliant part. Modern research is proving we can actually synthesize high-performance Cordierite from hazardous industrial waste. No joke, we're talking about using bypass cement dust, magnesite, and drift sands as alternative waste precursors. It's this ingenious zero-waste circular economy approach. We are quite literally turning industrial trash into a highly valuable, high-tech engineering ceramic. How cool is that? Now, once you have those raw materials perfectly blended, you have to fire them, a process called sintering. But remember earlier when I said it was tricky?
Cordierite has an extremely narrow thermal window to get this right. The sintering kinetics happen in 3 strict steps. First, dehydration around 800 degrees Celsius to essentially bake out all the structural water. Second, between 1200 and 1275 degrees, intermediate phases like mullite and cristobalite form. And finally, the true magic happens between 1335 and 1430 degrees Celsius, bulk crystallization into the pure cordierite matrix. If you overfire it past 1460 degrees, it melts. The entire batch is totally ruined. So, to manage this super tight window and prevent disaster, engineers will often sneak in chemical fluxes, things like tellurium oxide or sodium borate. These additions beautifully enlarge the sintering window and actually lower the required temperatures, which ultimately saves massive amounts of energy during production.
Moving on to Section 4, shaping the ceramic. So, you've got the perfect powder and the precise thermal recipe. How do you actually turn a brittle crystalline matrix into a complex, usable shape? This is where the engineering story gets super fun. Traditionally, manufacturers used extrusion. When Corning was developing this for catalytic converters, they pushed a thick, clay-like mix of polyurethane resin and water through complex metal dies to make these honeycomb shapes. It was so incredibly fragile that an engineer named Rodney Bakley had to invent a technique to literally float the freshly extruded honeycomb on a bed of warm air just to keep it from collapsing under its own weight before it dried. Actually, think about how crazy that is, floating wet clay on air. But fast forward to today, and we're using advanced additive manufacturing. With techniques like binder jetting and digital light processing, or DLP, we can 3D print cordierite into mind-bendingly complex diamond unit cells, mathematically optimized for fluid flow. We have literally gone from floating wet clay on air to curing liquid polymers with light.
All right, let's look at the real world in Section 5, from cars to electronics. Where do these shaped ceramics actually end up? Well, if you drive a gas-powered car, you have a chunk of cordierite sitting right underneath you. Modern automotive catalytic converters feature those extruded cordierite honeycombs with an unbelievable 900 cells per square inch. And the walls of these cells are just 3.5 mils thick, which, to put that into perspective, is basically the thickness of a human hair. Yet because of that near-zero thermal expansion we talked about earlier, these incredibly delicate, paper-thin ceramic walls can survive the violent thermal shock of your car engine starting up in the dead of winter and instantly hitting hundreds of degrees. It's an absolute masterpiece of extreme precision and everyday durability. But hey, cordierite is not just for dirty exhaust pipes. When it comes to high-frequency electronics, its properties are absolutely astounding. It boasts an electrical resistivity greater than 10 to the 14th ohm centimeters and a breakdown voltage between 5.5 and 10 kilovolts per millimeter. Basically, it's an elite electrical insulator. But the true star of the show here is its relative permittivity, or dielectric constant, which sits nicely between 4.1 and 5.4. That is vastly lower than alumina, which has traditionally been the go-to electronic ceramic. Because cordierite's dielectric constant is so low, electronic signal transmission through it is much faster and suffers from significantly less crosstalk. This makes it highly desirable for critical, cutting-edge applications. Think radar domes on aerospace vehicles and low-temperature co-fired ceramics used in super-advanced high-speed microelectronics. And finally, Section 6. The sustainable, high-tech future. The journey of this material is far from over, let me tell you. The cutting-edge research happening right now is thrilling. First up, the industry is fiercely tackling end-of-life recycling. They're ensuring that millions of discarded catalytic converters can actually be upcycled back into new, high-value products, instead of just sitting in a landfill somewhere. Second, material scientists are blending cordierite with potassium silicate-based geopolymers to create these awesome low-temperature composites specifically designed for high-temperature filters. But for sure, the most exciting leap is happening at the atomic level. Researchers are now literally inserting potassium ions directly into the structural channels of the cordierite crystal. By tweaking the ceramic atom by atom, they are fine-tuning its dielectric properties to serve as the physical backbone for the massive, high-frequency data loads of tomorrow's 5G and 6G networks. It's wild. So I want to leave you with this final provocative thought. We started with a mineral discovered over 200 years ago, and today we are literally inserting individual ions into its crystal lattice to transmit millimeter-wave internet. As we continue to manipulate materials atom by atom, how will cordierite redefine the absolute limits of tomorrow's technology? It's just a brilliant reminder that the most invisible materials often have the most visible impact on our daily lives. Thank you so much for joining me on this explainer, and keep exploring.